Okay. Good morning, everyone. Today, I'm very glad to talk about our work on a new metric learning model for multivariate time series, which is called DECADE, the Deep Expected Alignment Distance. So as we all know, the time series data is becoming ubiquitous nowadays, and also determine the similarity between the multivariate time series or calculate the distance of them is very useful and fundamental. For example, in healthcare, doctors want to know the similar patients of a new patient for better decision making and diagnosis. And also, given two voice clips, if we have a better time series similarity, we can know whether the two clips are from the same speaker or not. However, finding a good time series similarity for the multivariate time series is very challenging. For example, there are lots of complex temporal dependencies across the multivariate. And also, time series usually comes with variable lengths of the variable lengths, which makes some standard metric learning method that not work for time series data. And also, people have known that there's no universal similarity measure can work best across all the applications for the time series data. So here comes the question. Can we learn the data-dependent distance metric, which can be very effective without too much prior knowledge? The answer is yes. And we want, before we propose our new metric, we want to answer the questions. What makes a good similarity measure for multivariate time series? So here, we come up with 3 questions. First, what kind of local distance to use to compute the global distance? And how we align the time series when we want to calculate the distance? And finally, whether the global distance we get is a valid metric or not. To be more specific, whether the distance metric satisfies the triangle inequality, which means that the distance between the time series x and y and z should be no more than the distance of the time series x and z. So most of the existing work use a predefined local distance. However, as we mentioned before, the fixed local distance is not that powerful to capture the complex dependencies. So we prefer to use the flexible data-dependent local distance learned directly from the data. And also, some metrics do not take the pairwise alignment between the time series. However, the alignment between time series is very important since it contains the temporal relations between these two time series. So we also consider to take the alignment to calculate the metric. And finally, most of the existing metric are not the similarity, not the valid metric for time series data. For example, the dynamic time warping, which is commonly used, but it's not a valid metric. So this will prevent us from using this kind of similarity in some kernel methods or to use it in the first nearest neighbor search with theoretical guarantees. So we want our similarity measure to be a valid metric. So here is a summary of some commonly used time series similarities. As we mentioned before, the dynamic time warping, the MDTW, doesn't have the theoretical guarantee on its validity. And similarly, the global alignment kernel, GAK, has some constraints on its local distance so that it can be used as a valid kernel. And some other methods, such as the deep learning-based methods, such as LSTM, they usually take the last representation from the last time steps, so that the temporal alignment between the time series is not considered. So here comes our new similarity measure, the decade. So first, it has all the three desired properties. It has the data-dependent local metric, which can be learned directly from the data with only the time series and its labels. It considers the alignment between the two time series so that it can better model the temporal dependency and the relations. And finally, it is a valid global distance metric so that it can be used for kernel methods and for some other speed up methods for nearest neighbor search. And it only consists two indispensable components. One, which we call is expected alignment, and the other one is the deep learning based local distance called a kernel local distance metric. And we will also show that our decade is quite flexible and easy to train. It can be trained by any metric learning framework, given the time series and its labels. And here, we will use the large margin metric learning method as an example to show the effectiveness of our model. So here is just to remind that the decade is one model that can satisfy all these three properties. So before we introduce our metric, first I want to clarify some definitions and the notations of the time series, the alignment, and the distance on the alignment. So we use X to represent a multivariate time series with P features and of temporal length Tx. And given two time series X and Y, an alignment of A is a arrangement of the two time series at each time step. And it can be defined as a pair of non-decreasing sequences, alpha, beta. So for example, if the two time series have lengths Tx and Ty, and U is the length of the alignment. So every component of alpha and beta should be in the range of from 1 to Tx and 1 to Ty. And given an alignment and the time series xy, if we define a local distance dxy, which is defined at each time frame, is a function mapping of two p dimension vector to one positive value, then the distance between x and y on the alignment is defined as the summation of all the local distance along that alignment. So usually people will take the squared Euclidean distance or some other, or like cosine similarity as the local distance. And before we introduce expected alignment, let's see the dynamic time warping, which takes only the one single best alignment from all the possible alignments of the two time series. So we know that there are some issues from the choice of the one single best alignment. First, we know that the DTW doesn't satisfy the triangle inequality. And also, if we want to learn the local distance with DTW, we know that the alignment itself is non-differentiable if we train it use a end-to-end backpropagation training. So we either go with the alternative training, which optimize the alignment and the local distance alternatively, or we will be trapped in the local optima, and the training can be very inefficient. So our basic idea of the expected alignment is that we consider the average distance over all the possible alignment paths with a proper length, u, within the range of ul and uh. So first, we will show that the distance on the expected alignment can give us a valid metric. And also, we will show that the training on the expected alignment can be very effective with local distance. So the first thing is that we want to make sure this distance metric is a valid metric. So to be more specific, it should satisfy the non-negativity, the symmetry, and the triangle inequality. And the last one is the most important one, because most existing method fails on that. So in order to prove this triangle inequality, we can first consider the average distance. We can first fix the length of the alignment, and then we can regroup each local distance triplets, because the local distance itself satisfies the triangle inequality. And after we do this regroup and summation, then the final global alignment will also satisfy this. And given the original definition of the expected alignment, we can find if we want to calculate the distance, we need to enumerate all the possible alignments, and this can be very time consuming. So in order to fix that, we introduce another very simple and effective method, which is based on the sampling to calculate the distance on the expected alignment very fast. So the idea is quite simple. First, we uniformly sample the length of the alignment, and given the alignment of given the length of the alignment, we can uniformly sample all the alignments with that length from all the possible alignments. And we can also show that given our sampling strategy, the approximated distance is quite close to the ground truth expected distance. And even in our experiments, we can use even fewer samples to get the very close distance. And given the definition of the expected alignment, the next step is how we can learn the local distance very efficiently. Good thing is we have the powerful deep learning model, which can be incorporated to the expected alignment framework seamlessly. So here, we use the multi-layer feed-forward network as the transformation function at each time frame. And the network weights are shared across different time steps, so it can be treated as the recurrent neural network with no connection between time steps. And after we get the transformation, we take the squared Euclidean distance of the transformed vectors as the local distance. And finally, this can be incorporated in the expected alignment. And also in practice, we noticed that given our powerful framework, only a relatively small neural network with only 2 hidden layers can be effective enough on our datasets. And given the 2 components, the next step is how we can learn the metric efficiently. So here we take the large margin approach as an example to show that how the decade can be learned given only the time series and the labels. So here is the objective function to minimize. So basically, we have the part of the pairwise distance of the time series from the same from the same group or with the same label. So that we want to reduce the distance of 2 time series with the same label. And also we have another part so that we can increase the distance of the 2 time series with different labels. And also we can incorporate any regularizations of our model into the loss function as well. For example, the L2 loss or other weight regularization on the neural network. And finally, we can use the gradient training to train this. So we tested our model on 3 real-world healthcare datasets with different properties. So for example, on the PhysioNet and the ICU dataset, the time series are irregularly sampled, which better fits our condition. And also, in ICU datasets, the time series are of variable lengths. And also for the EEG dataset, we have more features than the time steps and multiple classes. So here is the results of the 1 year's neighbor classification accuracy. We can say that the decade achieves achieves the best result on 2 of the 3 datasets, and also is quite close to the best on the other one. And also, we want to show that the two components, the expected alignment and the local distance, are indispensable. So here's the nearest neighbor classification accuracy of the dynamic time warping, the decade, and the 2 variations of them. So the MDTWNN is the dynamic time warping plus the learnable local distance, and trained by alternatively optimizing the alignment and the local distance. And EA is the expected distance with a fixed local distance. So first, we can say that learning a data-dependent local distance always helps. And also, even though without the metric learning, the dynamic time warping performs better than expected alignment. But if we incorporate the learnable local distance, the decade achieves larger improvement than the dynamic time warping. So this is because that incorporating the local distance in the expected alignment, the training is quite effective. And we can say that these 2 components are necessary. Also, we will show some realizations of our results. So this is the realization from the embedding of the PhysioNet dataset based on the pairwise distance we calculated. So first, we can say that the red dots represents the patients with in-hospital mortality, and the green ones the rest of the patients. So first, the decade provides more clear boundary of the 2 groups. And also, because we know that for the patients with in-hospital mortality, their records usually comes with extreme or abnormal values. So our decade model can successfully spread out all the patients with the in-hospital mortality, which can be treated as anomaly samples, and while keep the normal patients centered in the middle. And here is the summary of our work. So here we proposed an effective metric for multivariate time series. It has 2 components. One is the expected alignment, and the other one is the learnable local metric. And so that it's quite flexible. And we also show that one important thing is there's the theoretical guarantees on the validity of this metric, so that it has its own advantage. And also, because we take the alignment of time series into the calculation, so that we can better capture the temporal patterns and correlations. Finally, we show that there's a simple and effective sampling-based approximation which can help us to calculate our distance more efficiently. And we also show the state-of-art performance on different data sets. So in the future, we want to say broader applications such as the hashing, embedding, or clustering. And also, we want to show that we want to do more empirical evaluations of the model variations and incorporate on different data sets from different domains. So that's it. Thank you.